Welcome to the lecture series of network theory. In our last few classes, we have seen series and parallel RL, RC and RLC circuit. We have seen the derivation of voltage, current, phase angle. We have seen their voltage and current waveforms, phasor diagrams, and we have also solved a few numericals. In today's class also, we will be solving a few more numericals based on RLC circuits. So let's get started. Let's start with the first one. Now in this network, as we can see, this is neither a parallel RLC nor a series RLC circuit. Rather, the connection of this network is slightly different. How they are connected? In this circuit, we have all the three basic components. But here in this branch, as we can see here, resistor and inductor, they are connected in series, and separately this resistor and capacitor are connected in series, and both those series connections are connected in parallel with each other. And with that connection, again this inductor is connected in series, and with that whole connection an AC voltage is applied. It doesn't need to be mentioned that this is a sinusoidal voltage. Now here the value is given as 100 volt. So this is the RMS value of that applied voltage, and since there is no mention of the phase angle, so that means this voltage will be taken as a reference, and the phase angle of that voltage will be 0 degree. So in polar form this will be the value. Now suppose if that voltage supplies a current I in that circuit. Now suppose that current after coming at this point, if in this parallel branch, if it gets divided into two parts, where through this series branch the current I1 flows and through this branch I2 flows. Now again these two currents will combine here at this point, and the main current I will flow through this inductor. Now let's first find the impedance of this series branch. Now if the impedance of that series branch we name as Z1, then that will be simply the resistance of that branch plus the inductive reactance of that inductor. So it will be J4, which is given in the problem statement, this much ohm. Now this is given in rectangular format. Now if we want to suppose want to convert it or represent it in polar format, then it either we can apply the formula or we can use the calculator directly, and that value we will get finally as 4.123, and angle will be 76 degree, and since this is impedance, so the unit will be ohm. Now let's find the impedance of this series branch, and if we name that as Z2, then it will be 3 minus J2 ohm. Now if we convert that to polar form, then it will be 3.61, and the angle will be minus 33.7 degree ohm. Now with this parallel connection, since this inductor is connected in series, so finally if we assume that the net impedance or equivalent impedance of this whole network is Z, then in that network, as we can see, Z1 is in parallel with Z2, and then the impedance of this path, since this is connected in series, so impedance of that component or of that branch will be simply added as per the rule. Now if we find first the equivalent impedance of this parallel branch, then as per the rule it will be simply Z1 multiplied by Z2 divided by Z1 plus Z2, and then with that, since this is in series, so this will be added. Now Z1 has value 1 plus J4, or we can use the polar form also, so it can be written as 1 plus J4 then multiplied by Z2 is 3 minus J2 divided by 1 plus J4, and then plus 3 minus J2, and then this J4 will be added and the unit will be ohm. Now these two values we are multiplying, and we know if the values are given in polar form, then it is easier for us to multiply those values. So in place of this values which are given in rectangular form, we will use the values in polar form. So it will be 4.123 and angle is 76 degree, and with that the other value which is 3.61 and the angle is minus 33.7 degree, and in the denominator we are just adding those two values, so it will be easier for us if they are represented in rectangular form, which is already given. So simply their real values will be added, so 3 plus 1 it will be 4, and their imaginary parts will be added, so j4 minus j2, simply it will be plus j2, and then here plus j10. Now 4 point, this is the r part, this is the theta part, and this is the r part, this is the theta part. So simply r parts will be multiplied with each other. So 4.123 will be multiplied by 3.61, and that value we will get as 14.88, and these angles will be simply added. It will be theta 1 plus theta 2, and theta 2 itself is negative. So finally, if we do theta 1 plus theta 2, then the angle value will come as 42.3 degree. And in the denominator we have this value which is in rectangular form. So now next we will divide these two values, so it will be better for us if we represent this rectangular value in the value which will be in polar form. So if we do that, then the value in the denominator will come as 4.472 and the angle will come as 26.57 degree, and with that we have j10 which we will be adding. Now 14.88, this r value will be divided by this r value 4.472. so if we do that, then that value will be simply 3.33, and this time we are dividing, so theta 1 it will be theta 1 minus theta 2, so angle value will be 15.73 degree, and then with that j10. Now these two values will be added, so we have to, for simplicity, we have to convert this rectangular form into its equivalent polar form, and that will be 3.205 plus j 0.903, and with that we already have j10. So finally the impedance value or the equivalent impedance value will come as 3.205, and the imaginary part if we add, then it will be j10.903, and now if we represent that into its polar form, equivalent polar form, then it will be 11.36 and angle will be 73.62, and since this is impedance, so unit will be ohm. Now our requirement was to find the phase difference between the applied voltage and total current. The applied voltage, that value is given, we know that value, and the net impedance of that network we have already obtained. So next, if we want to get the current value, we can write here. So current value will be, since the voltage value is given in RMS, so this current value will be also the RMS value. So I will be simply V divided by Z. So V here is 100 and the phase angle is 0 degree, and the impedance value is 11.36 and the angle is 73.62 degree. Now if we divide 100 by 11.36, then it will be 8.8, and here we have 0 degree, so it will be 0 minus 73.62, so finally it will be 73.62 degree, and since this is current, so the unit will be ampere. Here we notice one thing, that the phase, this is the phase difference. So phase difference between the total current which is supplied by this applied voltage, the phase difference is minus 73.62 degree, and that means the net current I is lagging the applied voltage V by 73.62 degree. Now we know that in case of inductive circuit, the current lags voltage, and if it is pure than 90 degree, otherwise if it has some resistance associated with that, then it will be less than 90 degree, but still current lags voltage. So since here in this whole circuit the net current is lagging the applied voltage, so we can say here the net effect of this circuit will be inductive, though we have a capacitor here. Now value wise also, if we see here, we can see that we have two inductors, and their values are J4 and J10, their reactance values, and we have only one capacitor, and that reactance values is also minus J2. So from the value itself also, this is obvious that the inductive effect will be more in this circuit than capacitive effect. And this value wise also, we have proved that the phase angle is negative, so the current is lagging the applied voltage. Now we will move on to the next problem. Now in this circuit, as we can see, we have two parallel branches, and in every branch we have two components connected in series. In this branch, a resistor and capacitor connected in series, and their resistance and capacitive reactance values are given. And in this circuit we have the resistance value, and this inductor and resistor are connected in series, but the inductive reactance value is not given, rather it is represented by x suffix L. And this parallel branch is energized by an AC sinusoidal voltage having value 100 volt. Now this 100 volt definitely is the RMS value of the supply voltage, and that we can take as 100. And since this is the common factor between these two parallel branches, so this will be taken as a reference, so the phase angle will be 0 degree here, and that's why it is not mentioned. And the current which is supplied by this AC voltage, that value is also given, which is 10 minus 30 degree ampere. So from this value minus 30 degree ampere, we can say that the phase difference between the applied voltage and the total current is 30 degree, and the net current is lagging the applied voltage by 30 degree angle. That means even though we have a capacitor in this circuit, by the net effect of that circuit or AC circuit is inductive. Now the values that are given, based on that, if we find the impedance of this branch, then it will be 20, and then the capacitive reactance value minus J10, and that much ohm. Now if we convert this value which is given in rectangular form into its polar form, then it will be 22.36, and angle wise it will be minus 26.57 degree. Definitely this angle will be negative angle, as this is capacitive circuit, so the current in case of pure capacitor leads the applied voltage by 90 degree, and if we have a resistance, then that phase angle will be less than 90 degree. Now current is, as we know, is found by this formula V by Z, and since current is leading the phase angle of the current, so definitely the phase angle of the impedance should be lagging in nature. Now if we find the current value I1 based on the voltage and the impedance that we have calculated, voltage value is given and impedance of that path we have calculated. So voltage value is 100 and then 0 degree, and the impedance value is 22.36, and angle value is minus 26.57 degree. So this two value 100 will be divided by 22.36, and that value will be 4.47, and this 0 degree, from this 0 degree we will subtract this angle which is itself is negative. So finally the angle that we'll be getting, that will be positive in nature. So that's why we can say that the current in capacitive path will lead the applied voltage, and that's why here the phase difference is positive. Now this much ampere, the total current is given. So if we mark this current as I1, then definitely the current in the second branch of that parallel circuit will be I minus I1. Now the current value in that second branch we can find this way, that it will be I minus I1. So I value is given as 10 and then minus 30 degree, and I1 value we have obtained as 4.47, angle 26.57 degree, and that much ampere. So now since we are subtracting these two values, so it will be easier for us if we convert them into rectangular form. So if we convert 10 minus 30 degree, then that will be 8.66 minus J5, and this value will give us a value as 4 plus J2. Now this both the values are represented in rectangular form. Now these real values can be easily subtracted, so it will be 4.66, and then these two values, the imaginary parts of those two values, they are negative, so they will be simply added. So with that we will have a negative sign, so 5, and here we have 2, so it will be finally minus J7, and this much ampere. So this is basically I2, or the current in the second branch. Now again, this current in the second branch we can obtain if with that we mark as I2, then it will be again V divided by Z2, the impedance of that branch or that path. So V is same, that is 100, and this will be 0 degree, and Z2 will be simply, since these two components are connected in series, so it will be R, which is given as 6.5. So it will be 6.5, and this is inductor, so inductive reactance, that will be taken as JXL, this much ampere. So these two values definitely are same. I minus I1 will be equal to I2. Now if we equate these two values, then it will be, we can write this way, or we can write 6.5 plus JXL, that will be equal to 100, which is the value of the voltage, divided by the current value, which is 4.66, and angle, this is given in polar rectangular form, so J7, and this is the value of the impedance of the second branch. Now 100, 0 degree, this is given in polar form, and this needs to be converted to its equivalent polar form. So if we do that, then we will be getting a value like 8.41, and angle will be 56.35 degree. So now if we simplify further, then 100 divided by 8.41 will give us a value as 11.89. Then angle will be 0 minus of minus 56, so finally it will be plus 56.35 degree, this much ohm. It is given in polar form, so now if we convert to rectangular form, then it will be 6.59 plus J8 9.9 ohm. So this is the impedance of the second branch, and which is given as, here as we can see, it is 6.JXL. So if we equate the resistance and the reactance part of both the sides, then it will be nearly equal to, this is 6.5, which is also 6.59, so they are almost same. And the reactance part, if we equate them, then we can straightforward write that XL will be equal to 9.9 ohm in this circuit. So this is the way how we can simplify this circuit, which has all the components R, L and C, but they are neither directly connected in series nor directly connected in parallel. Now next we will see and solve another numerical based on a series RLC circuit, but here the format is different. In this circuit, the value of the resistance, the inductive reactance and capacitive reactance, these three values are given. The series RLC circuit is energized by an AC sinusoidal voltage Vs, where the instantaneous voltage notation is given here. Now let's assume that this voltage source supplies a current I, which is again, this is the notation of instantaneous current. Now there is another parameter of value which is given, and that is the voltage difference across the inductor. That means this voltage difference is given VL, and that is 100 cos 20t plus 45 degree. Let's assume that the voltage difference across the capacitor is Vc and across the resistor is Vr. Now why it is different? First of all, the expression of the instantaneous voltage drop across the inductor, that is not given in the form of sinusoidal, rather it is given in the form of cosinusoidal. And we know in case of pure inductor, the voltage across the voltage drop across the inductor, that leads the current that flows through that inductor by 90 degree. But here that phase angle is given as 45 degree. That means the reference that we take, with respect to that reference, the VL, the voltage drop across the inductor, is leading by 45 degree angle. That means the current through this inductor will be lagging by minus 45 degree with the reference. Then only the total phase difference between the voltage drop across the inductor and the current that flows through the inductor, that will be 90 degree. So that means we can think this way, that if this is the reference, this horizontal line, then this will be our VL, which leads the reference by 45 degrees. So this is plus 45 degree, and definitely the current that flows through that inductor, so that will lag that reference by minus 45 degrees. So this will be IL, or simply we can say I, since this is a series RLC circuit, so same current will flow through all the components. So this is, with this reference, the voltage across the inductor is leading by 45 degree, and the current through that inductor is lagging by 45 degrees. So 40 plus 45 plus 45, in total it is 90 degrees. So the total phase difference between this voltage and current will be 90 degrees. So that is satisfied. So based on this format or this value of the instantaneous voltage drop across the inductor, we will proceed further. Now if we want to get the RMS value of that same voltage drop across the inductor, then that we can achieve or obtain this way, that since in this format this will be the maximum or peak value of that voltage drop. So we know that when we divide the maximum value by root 2, then we get the RMS value. So it will be, in case of VL, it will be, if we want to have the RMS values, then it will be 100 divided by root 2. This is only the value. Now if we want to represent in polar form, then it will be, we have to consider the angle also, which is 45 degree, the phase difference. So finally if we simplify this, then it will be 70.7, and angle wise it is 45 degree, and since this is voltage, so it will be volt. Now if we want to get the same value in rectangular form, we can convert that easily. But next what we will do is we will calculate the current which flows in this series circuit. So that let's denote that as IL. So here simply it will be VL divided by the reactance of that inductor, or inductive reactance. So VL we have calculated as 70.7, then 45 degree divided by XL is given as J10. Now J10 is given in rectangular form, so that needs to be converted to polar form for simplicity. If we do that, then it will come as 10, and since we don't have any real part here, so simply it will be 0 square plus 10 square and square root of that, so it will be 10 only, and because of this J, the angle will be 90 degree. So finally that value will be 7.707, and angle wise it will be 45 minus 90, so minus 45 degree ampere. And as I said, that the current which flows through the inductor, that will lag the reference line by lag by 45 degree, or the phase angle will be minus 45 degree, so that the total phase difference is 90 degree. Now since this is series circuit, so we can say that the current through inductor will be equal to current through resistor, and that will be equal to current through capacitor. Now based on this current, next if we want to get the value of VC and VR, easily we can obtain that. Now in case of VR, it will be simply I multiplied by the resistance value. I means IR or IL, that is 7.07, and angle is minus 45 degree, and this will be multiplied by the resistance value, which is 10. So it will be again 70.7, and angle wise it will remain same, that will be minus 45 degree, and this much volt since voltage. Now next is to get the value of the voltage drop across the capacitor. So it will be again the current value IC, which is same as IL, so it will be 7.07, and angle wise it will be minus 45 degree, and that will be multiplied by the reactance value of that capacitor, Now the reactance value is given in rectangular form, so that needs to be converted to polar form for simplicity. If we do that, then it will be 7.07 minus 45 degree, and for the reactance part it will be 2 value wise, and because of this minus j it will be minus 90 degrees. So after simplification it will be 7.07 multiplied by 2, simply it will be 14.14, and angle wise these two angles will be added. So both the angles, they themselves are negative, so it will be finally minus 135 degree volt. So all these individual voltage drops, their RMS values we have obtained. Now since we have to find the instantaneous value of the total voltage, so first we will get the RMS value of the total voltage. So it will be simply addition of these two individual voltages. So Vs will be Vr plus Vl plus Vc. Now Vr we have obtained as 70.7, angle wise minus 45 degree. Then for Vl this is 70, again 70.7, angle wise this is 45 degree, and Vc it is 14.14, and angle wise it is minus 135 degree. And it has to be minus 135 degree because the net current in that series circuit, that is lagging the reference by 45 degree. And in case of pure capacitor, the voltage drop across the capacitor lags by 90 degree, lags the current that flows through the capacitor by 90 degree. So this is 90 degree, this is Vc. So this Vc, voltage drop across the capacitor, will lag the current. This is IL, and that is also equal to IC. We have seen that. So this Vc will lag IC by 90 degree, and IC again is lagging the reference by 45 degrees. So in total it will be 90 plus 45 degree is 135 degrees. So this Vc will lag the reference by 135 degree. That's why it is minus 135 and this much volt. Now since we are adding these three values, so it will be better if we convert all the values into rectangular form. So after representing in rectangular form, we will be getting these values. So it is 70.7, then cos theta plus j sin theta. So cos of minus 45 degree, that means cos of minus theta is equal to cos theta, so cos 45 degree only. And plus j sine of minus 45 degree, so it will be minus sine 45 degree, that means minus j sine 45 degree, and that rule we have applied for other true values also. Then if we put the values of cos 45 degree and sine 45 degree, then it will be 70.7, and then cos 45 degree is 1 by root 2, and sine 45 degree is also 1 by root 2. And from here this j sine 45 degree and this minus j sine 45 degree will cancel each other, as we have this constant value 70.7 in both the cases. So this will be finally the same values. Now here from these two values we have 70.7 and cos 45 degree, this because this is coming twice, so it will be 70.7 2, and then cos 45 degree itself is 1 by root 2, and with that we have 14.14, and cos 135 will give us a negative value, which will be minus 1 by root 2, as it lies in the second quadrant, so negative. And then we have minus 14.14 sine 135 will have positive value, and value wise it is 1 by root 2 again. Sine 135 will be the value, will have the value of sine 45 degree only. 135 will be equal to sine 45 degree, and in the second quadrant sine has positive value. So finally if we simplify this, after simplification finally we'll be getting value as it will be 100 minus j20, and that much volt, and this is given in rectangular format. So after simplifying all these three values, now if we convert this value in rectangular form into its equivalent polar form, then it will be 102, and angle will be minus 11.3 degree, and this will be V. So this is the phase difference between the applied voltage and the total current that flows through that series RLC circuit. Now if we represent the instantaneous value of that source voltage or supply voltage, then it will be Vm, the maximum value. Now here this is the RMS value of the source voltage, so maximum value will be 102 multiplied by root 2. As we know, RMS is equal to peak divided by root 2, so this much. And then here the VL was represented in the form of cosinusoidal, so for VS also we will represent in the form of cosinusoidal, so it will be cos omega t, and then the phase difference, so this will be the 11.3 degree. But this 11.3 degree, this voltage difference will be with respect to the reference, as the for other values we have represented with respect to reference only. So for here, this phase difference, this lagging phase difference will be with the reference line. So finally it will be somewhere here, so it will be lagging in nature, and value wise it is 11.3 degree and this much volt. Now if we simplify further, then 102 multiplied by root 2, that will be 144.25, and then it will be cos omega t minus 11.3 degree, this much volt. So in this circuit we see that the phase difference between the reference line and the source voltage is 11.3 degree, and the phase difference between the reference line and the supply current is 45 degree. That means the phase difference between the source voltage and the supply current will be 45 minus 11.3 degree, and here we can see that the net current is lagging the supply voltage. So here the net effect of this circuit will be inductive. So with this I end today's class. Thank you.